This is the teaser for my paper Intuitionistic Euler-Venn diagrams. As the title suggests, it's about Euler-Venn diagrams with an intuitionistic semantics. The motivations for defining such a language is that the intuitionistic logic itself has interesting properties. It connects to different mathematical theories in very subtle ways. For example, formulas of intuitionistic logic correspond to types and proofs to programs, and the semantics of intuitionistic logic can be given in terms of open sets of topologies. But many classical laws do not hold, in particular, the logical operators like disjunction and conjunction are not interdefinable. The topological semantics suggests to exploit topological relations for a visual reasoning system. This brings us to Euler-Venn circles, which are using exactly these relations to express properties of classical logic. However, they crucially use that classical reasoning only needs a small set of logical operations. In particular, shading of zones is used to express negative information and is equivalent to omitting zones. For example, the diagram on the left expresses that A and not B cannot be true together, which is classically equivalent to A implies B depicted on the right. The problem is that these two statements are not equivalent in intuitionistic logic. So we first need to define a suitable semantics for Euler-Venn diagrams with respect to intuitionistic models. As such a model, we will use Heyting algebras. One of the main changes from the classical interpretation is the interpretation of shading. Here it will mean that the corresponding element of the semantics can be constructed. We start with a diagram where all possible zones for a set of contours need to be visible. In the diagram here, the upper shaded zone denotes the meet of A, B and the intuitionistic complement of C. The whole diagram then represents the join of the elements denoted by the shaded zones. However, this does not allow us to express intuitionistic implication, so we need additional syntax for this purpose. We will use diagrams with dotted contours and where no shading is allowed, but we do allow for the omission of zones. Then we can express implicational information in a similar way to classical Euler diagrams. Here, for example, the missing zone that would be within A, B and C represents that the meet of A, B and C implies false and hence the complement of this element. We'll call the first type of diagrams pure Venn diagrams and the other pure Euler diagrams, because they only use the syntax typical for these types of diagrams. But to have a connection between the two types of information, we also will use a combination of both. This is done by allowing for both shaded and missing zones, and we will interpret such a general Euler-Venn diagram in the following way. The information of the missing zones implies the information denoted by the shaded zones. To reason with such a system, we need to define suited proof rules, and we'll do that in the way of a sequent calculus for such diagrams. Here's an example of a rule reducing pure Euler diagrams. The interesting part is that it allows us to remove contours from the diagram while keeping the topological information. However, the rule is only applicable under certain constraints. In the paper you can find the full set of rules. This set is both sound and complete, and the proofs are indicated in the paper as well. Furthermore, the typical structural rules of contraction, weakening and cut are admissible in the system.